Uh, I'm trying something new here. I've got my little pad and electronic pen, and I've got a Microsoft Word document open where I can use it as a whiteboard, and I've got Excel open as well. So if we can toggle between Word and Excel and do some calculations, and we'll use a PowerPoint to bring the concepts more to life. So the first thing is some terminology. Probability is a measure that we talked about before that looks at the outcomes of particular events. And that the events are not guaranteed, but they're selected from an option. So in statistics, they call it an experiment. It's a planned operation carried out under some controlled circumstances or conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. So it's not predetermined, and we're talking about where, like flipping a coin or rolling a dice, you don't know what's going to come out. You know what the possible outcomes are, but you don't know which one is going to happen next. Flipping one fair coin twice is an example of an experiment. The result of the experiment is called an outcome or an event. The sample space of the experiment is a set of all possible outcomes. The uppercase letter S is used to denote the sample space. So if you flip a coin, S is equal to the set of head and tails, where H is flipping a head, and tails is obviously flipping a tail. So an event is any combination of outcomes. Uppercase letters are used like A and B. So S is the set of all possible outcomes. A are particular outcomes that we're looking at. So if you flip a fair coin, one event A might be getting at most one head. Well, if the experiment is to flip one fair coin, it's at most one head. The probability of A is written P of A. The probability of an outcome is a long-term relative frequency of that outcome. What do we mean by long-term? If you do it an infinite number of times, what is the long-term relative frequency of that? And we remember what relative frequency is from our chapter 1. So probabilities are between 0 and 1 inclusive. That is, means 0 and 1 are part of the numbers of these values. And they can be anything between 0 and 1, depending on the number of decimal places you want to go. Also, if you multiply by, so these are decimal places. If you multiply by 100, they become percentages, and percentages and decimals are just the difference between two of them is decimals to percentage are multiplied by 100. Percentage back to decimals is divided by 100. So 0%, 100%, 50%, or 0, 1, and 0.5. Equally likely means that each outcome of an experiment occurs with equal probability. If you toss a fair coin, the probability of head and the probability of tail is equally likely to occur. So if we look at our Word document and see how this bad boy works, if I go here and pick this, and say draw and pick that. Let's see if this actually works. Yes, it does. And now I draw like someone with palsy when I use this. So the set is equal to head and tail. The probability of getting a head is 1/2, which is equal to 0.5, which is equal to 50%. The probability of getting a tail is also 1/2, 0.5, or 50%. Which way do you want to draw it? It really depends on what you're trying to do. The homework I would think if you're doing it in Excel, decimals or percentages, if you're handwriting it out, I can deal with fractions. Make sure you put fractions in the lowest terms. Okay. So, flipping a coin is equally likely occurrence. To calculate the probability of an event when all outcomes in the space are equally likely, you count the number of times outcomes for an event A. What are the number of possible outcomes that fit your event A, and divide by the total number of possible outcomes in the sample space. So if we're tossing a fair coin, a fair dime and a fair nickel, so when we say dime and nickel, and that means we're recording the dime first and the nickel second, so we're distinguishing between the two coins instead of flipping a coin twice, which is basically, it's a slightly different thing. The space is heads, 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 tail, and tail, tail. The outcome has four outcomes. So let A be the equal getting one head exactly. Well, there's only two outcomes where you get one head. It's the middle two. It's this, and I guess I can underline things, and I hope it stays with the slide and doesn't come. Oops, not that one. It's that one. Let's get rid of that, or I could go up here and just actually erase it. Okay, so it's those two. So there's two outcomes that do that. So the probability is 2 divided by the total number, which is 4, or I get 0.5. Now, there's something called the law of large numbers. This says if I flip a coin over and over again, if I flip a coin 3-4 times in a row, I might get all heads, I might get all tails, I might get a mixture of both. But if I do it over and over and over again, ad nauseum, and to an infinite number of times, the probabilities of getting a head and a tail are going to converge very close to several decimal places, probably hundreds of decimal places, to being close to 50%. Even though the outcomes do not happen according to any set pattern or order overall, the long-term observance relative frequency will approach the theoretical probability. So I don't really know that if I take any coin and I flip it, it's going to be 50-50. We count on that being true because of this law of large numbers. Some statisticians, some quality people, W. Edwards Deming being one of them, would say that you don't know. You actually have to run the experiment and you have to do it over and over again. But if it goes to 5 decimal places after you do 500 of them, I'm okay with that. That's close enough for flipping a coin to see who gets to kick off in a football game or who gets to receive the ball and what end zone you want to defend. So there's or and events. An outcome is an event A or B. If the outcome is A or is B, it means it is A or is B or both A and B. So this comes out to have some concept that we talked about in class about so 1, 2, 3, 4, 5, and 4, 5, 6, 7, 8. Let's remember that. Let's go over here and look at what we've got. And I've got to, let's change the color slightly. Okay. Event A was, and of course, short-term memory is the first thing to go. So it was 1, 2, 3, 4, 5. The number is 1 and 3, 4, 5. B is 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. And we list the things in these brackets, and they're called sets. And the elements, the different elements are separated by comma. If I didn't separate it by a comma, that would be 56. So A or B. It means it has to be part of A or B. A goes to 1 to 5, 4, B goes from 4 to 8. So really, if I do both, I don't count 4 and 5 here and 4 and 5 here are the same. So really, this is 1, 2, 3, 4, 5, 6, 7, 8. That's a horrible bracket I just drew. Another way of saying this is A or B. This symbol here means a unit. So this is set notation. A is a set of those 5 elements. B is a set of those 5 elements. They could be different lengths. But when I say let's take the union, I'm dumping all the elements of both sets into a new set, and there's no double counting. So this has 5 elements. This has 5 elements. The resulting has 8 elements, which means the number of there was 2 that they shared in common. If I do the number of A, that says how many elements are in A? 5. Number of elements in B equals 5. Number of elements in A union B or A or B is 8. Okay, so let's come up with a new page here. See, how do I do that? I'll just raise it up a little bit. Okay, now the next thing you can do is you can do A and B. Well, this means it's not in A and it's not in either or both. It means it has to be in both. And this is a upside down view, which means intersection. It means only the things they have in common. Well, the only elements they both have a 4 in it. There's no 1, 2, or 3 in B. There's a 4 and 5 in both. And there's no 6, 7, or 8 in A, so that's it. The number of elements here equals A intersection B is 2. So what do we have? The number of elements in A union B plus the number of elements in A intersection B equals the number of elements in A plus the number of elements in B. So let's go here. What do I want to do? I want to insert. If I can do that. Oh, I'm doing the wrong thing. Insert blank page. So I'm creating a new page up here. So let's go back to draw. I'll go back to my turquoise color. If A intersection B has no common elements, we say it is the empty set. You do it like symbolize it by that, or a set with nothing in it. The number of items in the empty set or the null set is 0. So if there is no intersection, A union B. It means its sets are separate and distinct. So here's the or and. You can look at that. The complement of A is denoted as A prime and consists of all outcomes that are not in A. So notice that the probability of A and the probability of A prime equals 1. So let the sample set be the numbers 1 through 6, and the event A is 1 through 4. So it's like rolling a dice, and I have to get a 4 or less. Well, that's a probability of A, and what would that probability be? If this is rolling a dice and the dice are all even, what would I get here? I get the probability of A equals the number of items in A, which goes with our count before. So we had 4 events, or out of 6 total. So I get 2/3. A prime is 5 and 6. It's not getting A. So the probability of A prime, which is like apostrophe, is 2 out of 6, or 1/3. And if I look at adding 2/3 and 1/3, what do I get? I get 1. So it's exactly what it is saying there. Conditional probability is the probability of A given that something B has already happened. And you write it probability of A with a like straight up and down slash B, and you read that as A given B. It's the probability that event A will occur given that the event B has occurred. A conditional reduces the sample space. So we calculate the probability of A from the reduced sample space B. So we say the formula to calculate A given B is probability of A given B equals the probability of A and B divided by the probability of B, where the probability B is greater than 0. If there's no elements, if there's no items in B, you have the empty set, so you can't divide by 0. I don't care if it's probability, statistics, geometry, or algebra. Okay, so here's an example. Flip 2 fair coins. This is an experiment. We don't care that the one's a dime and one's a head. The sample space is HH, HT, TH, TT, where it equals tails and heads. The outcomes are those following, those letters that we just talked about that are in that set. The outcome HT and TH are different. HT means that the first coin showed head and the second coin showed tails. The probability TH means that the first coin showed tails and the second coin showed heads. Let A be the event of getting at most 1 tail. So at most 1 tail means 0 or 1 tail. Find the probability of A. Well, how do you do that? Well, let's go back over here and draw a line, and we'll go back and forth. So what is A? A equals at most 1 tail. So it's HH, which is 0 tails, HT, which is 1 tail, and TH, which is 1 tail, but not TT because it's more than 1 tail. So there's 3 elements in this set. So what's the probability of A happening? It equals 3 divided by 4, or 0.75, or 75%. What's the probability of B? The event of getting all tails. Well, the only way to get all tails, and B would be equal to tail, tail. So the probability of B, there's only 1 of those, and it equals 0.25. So you could say A and B are complementary to each other, right? A prime is actually equal to B. D, the event of getting more than one tail. Well, the only probability of getting more than one tail is more than one means not equal to one. It has to be more than one. Is the same. D and B are exactly the same, are they not? This is where it gets a little confusing. E, the event of getting a head on the first roll. This implies that you get either a head or tail in the second roll. What's the probability of E? So in this case, if we go here and we look at E is the set of, and what was it again? Getting a head on the first roll. The only way we can do that is head, and head, tail. So there's two things there. So the probability of E is 2 divided by 4, 1/2, or 0.5, which is 50%. Let F be the event of getting at least one tail in 2 flips. Find the probability of F. So what does F all of a sudden look like? So F, wow, that's probably the nicest letter I've written the whole time. What was it again? Getting at least one tail. Well, that means it's head, tail, tail, head, and tail, tail. I can't believe, we're grown-up people talking like this. Head, tail, head, and tail, tail. What's the count of that set? The number of items in it are 3. So our probability here of getting F is 3/4, or 0.75. Try this. A bag, there are 6 red marbles and 4 green marbles. The red marbles are marked with the numbers 1, 2, 3, 4, 5, 6. The green marbles are marked with the numbers 1, 2, 3, 4. And R is the event of getting a red marble. Green is, or R means a red marble. Green means a green marble. O means an odd number marble. So the sample space is R1, R2, R3, R4, R5, R6. So that represents red marble with the numbers 1, 2, 3, 4, 5, 6. G is green marble with the numbers 1, 2, 3, 4 on them. So that's the sample space. S has 10 outcomes. What's the probability of green and odd? Well, let's look at it here. We can actually write this here because, and it's going to come out red, I suppose. So green intersection odd. So I'm not writing it. That means and. What's that set look like? It's G1 and G3. The probability of green intersection odd, and it's hard to distinguish between an O and a 0, so you got to be careful about using O as a delimiter. So there's how many items are in that intersection? There's 2. And what's the total number of outcomes? 10. Well, we have to reduce that to 1 out of 5. Or in this case, it becomes 0.2 or 20%. So try it. The sample space is a set of all ordered pairs of whole numbers. The first from 1 to 3, the second from 1 to 4. Well, you've got to list out those sets. Give it a try. We haven't done, now they're getting into conditional probability. So, I don't know, we didn't look at conditional probabilities here. What's the probability? Let's look at a conditional probability here. probability of getting, and let's give this something, a number. Let's give this a name. Let's call this just GO. Green odd. What's the probability of green, sorry. Let's erase this a little bit first. Let's not erasing. Green, let me go back here. Given that I got odd. Well, how many ways, what did they say this was? So if I go here, was conditional probability. It's A and B given the probability of B happening. Okay, so this odd really got written badly. Sorry. This is a nice little device, but I have a hard time getting everything done with this stroke eraser. Let's get rid of this. Let's get rid of that. And let's go back and write that better. Odd. Okay. So how many ways can I get green and odd divided by how many ways can I get odd? So how many odd ones are there? 1, 2, 3, 4, 5. There's 5 of those. How many ways can I get green and odd? We said there's 2. So 2/5 or 40%. So it's twice the probability of that. The probability of just getting green and odd is getting G1 and G3 out of all 10 of those things. But when I say, what's the probability of getting a green one given I got an odd? Well, now I've reduced my sample size to the following. I've got this one, this one, this one, this one, and this one. Those are the only odd numbered ones. So there's 5 of them. So instead of 10, I'm only worried about half the numbers. And how many of them can be green? 2 out of the 5. That's how that works. So I'm going to let you do this exercise yourself. Now let's talk about independent and mutually exclusive events. Determine if 2 events are mutually exclusive. Determine if they're independent. They're 2 different things. Calculate the conditional probability rules to calculate probabilities. Well, 2 events are independent if the knowledge that one occurred does not affect the chance of the other occurring. In other words, if the 2 outcomes of a fair die, if I roll a die twice, or flip a coin twice, it doesn't matter if the first one was heads, the second one to be head or tails is not going to influence that at all. And when this is the case, that the probability of A given B occurred becomes just the probability of A, or the probability of B given A occurred equals the probability of B. Remember that the probability of A given B is A and B divided by the probability of B. So for that to be equal to that means that the probability of A and B is equal to the probability of A times B. they happen, you multiply the two together. How does that work? Well, basically it becomes this. And let's advance this page a little bit. Draw a line here. What do we say? The probability of A and given B equals the probability of A and B divided by the probability of B. So if you go back to our other example of this example, let's go back here and let's look at this. What's the probability of green and odd? What do we say that was? That's going to be 2 divided by 10. And we want to divide that by the probability of odd. Well, that's going to be, how many odd ones were there? There was 5 out of 10. So the way this works is it becomes 2 times 10. And what do you do when you divide by a hold on, I'm getting a call that I got to tell them I'm going to call you later. I want to invert and multiply. Oh my God, I got to remember fractions. Since it's all multiplication, the 10s cancel out, and I just get 2 over 5. Or I get my 20%. So that works. Now you got to be like freaking out at this point because like, how does this work? So I've got that. Now if I'm saying they're mutually exclusive, oops, I don't mean to do that at all. Let's see, how do I undo things? There we go. I don't know what happened. But let me make this. Let's say if they're mutually exclusive, the probability of A given B is just the probability of A. Multiply both sides of this by the probability of B, and for mutually exclusive events, the probability of A and B equals the probability of A times the probability of B. Okay. So now I can start using this to do some calculations. If two events are not independent, they are said to be dependent. If it is not known whether the probability of A and B are independent or dependent, assume they are dependent until you can prove otherwise. Now, let's go back to this. So this means if they're independent. If they're dependent, it's not equal to this. I can only keep this part of the equation here. So if they're dependent, God, that's the worst handwriting ever. What does that mean? It means this. Probability of A given B times the probability of B equals the probability of A and B. So here we take, remember I told you probability starts with very simple concepts and gets very complicated very quickly. So what's the difference between these two formulas? Well, they're exactly kind of the same. This becomes this if the probability of A given B is the probability of A, which means they're independent. But if they're not independent, I have to write it this way. Okay? So what do we want to do? We want to go up here and say insert a blank page so we can continue our work here. Now, this is, you can't learn this by just sitting here and listening to my confusing lecture. You've got to actually work some problems. So let A be the event learning Spanish. B equals event learning German. A and B is learning Spanish and German. Can that happen? Well, of course, you can take two languages at once. Suppose P of A is 0.4 and P of B, and I would have picked S for Spanish or SP for Spanish and G for German. Why would I want to name them independent weird things like A and B? And here's what they say. Suppose the probability of a student taking Spanish is 4, and the probability of a student taking German is 0.2. The probability of A and B is point A. Are the events A and B independent? Well, what if I multiply point A times point B? What if I multiply point A times point B? Probability of A times probability of B. 0.4 times 0.2 is 0.008. Remember multiplication of decimals. I multiply the two numbers and I count the number of decimal places. So I multiply 4 times 2 is 8. Count the number of decimal places from, so I have 0.4 times 0.2 equals 8. And then I count 1, 2 decimal places and make it 0.8 because there's one decimal place here and one decimal place there. Given that this has happened, the probability of A and B equals the probability of A times B, I know that they're independent. So the probability, and I can conclude the probability of A given that the student takes Spanish is the probability of A, and the probability of B given the student takes taking German given he's taking Spanish equals the probability of just taking German. I can conclude that they're independent. Now, there's sampling with and without replacement. With replacement means every member of the population is replaced after it is picked. When sampling is done with replacement, the events are considered to be independent. What do we mean by that? Okay. The best way to illustrate this is using playing cards. So let's talk about cards. Okay, what is my issue here? I got to go back to draw. And let's use black this time. Okay. So I've got cards. Wow, this is a much bolder. Let's say event is getting an ace. Okay. On one draw. So what's the probability of getting an ace? How many aces are in the deck? There are 4 aces in the deck out of 52. And what is that? 1 out of 13. Because 4 goes into 52 13 times. If I was to do that calculation, I open up my calculator and I do 1 divided by 13 equals 0.07692308. Let's make it 0.077. And if I want to say that it's an approximation, I can make a squiggly one and 0.077. Okay. Now let's say I put that back and I calculate, again, I put it back, shuffle the card, I put whatever card I pick, I put it back in the deck and shuffle it again. Well, this is with replacement. I replaced the card into the deck, shuffled it again, made sure it was random, picked another card. What's the probability of picking an ace the second time? Well, it's still 4 out of 52 or 1 out of 13 or 0.077. Because I replaced the card. Nothing changed. The numerator and the denominator did not change. And let me enhance this with color. this doesn't change, and this doesn't change. So with replacement, I get the exact same thing. Now, let's say I pick 2 cards and I don't replace it. Let me make it less bold. Maybe bold is good, I don't know, let's see. So the probability of picking an ace the first time is 4 out of 52, which is 1/13th, which is 0.077. And this is the first draw. The probability of getting an ace the second time, let's call it ace on the second draw. Well, this is weird because I have 2 possibilities. One possibility is the probability of getting an ace on the second draw, given that I picked an ace. This is where conditional probability on the first draw. Well, how many aces are left? If I picked one and I didn't replace it, there's 3 left. How many, and I didn't replace 1 card, I get 3 out of 51. There's no reducing that fraction because that is 2 prime numbers, and 3 divided by 51 is 0.0588 or 0.059 approximately. Let's make it 0.059. 0.059. Also, or I have this. The probability of getting an ace the second time, given that I did not get an ace the first time, A prime. What is that? Well, now there's 4 aces still left in the deck, but so whatever card I took out, there's not 52 anymore, there's only 51, so it's going to be slightly higher. So what is 4 divided by 51 is 0.078, approximately 0.078. So I got 0.078. So with replacement, let's make this a different color so we can have fun. This is with replacement. The probability of getting an ace every time is the same, 0.077. If I don't replace the card, this is without replacement. Without replacement. I can't write, but that's okay. You get the picture. Okay. Playing cards is the best way. Also, having the marbles in a hat or a sack or a box that you pick different color marbles out. If you replace them, it's one thing. If you don't replace them, it becomes the other thing. It becomes the numerator and denominator change each time you do the replacement. Without replacement. Each trial that you do. Boy, oh boy, I confused myself. Let me say it again. If you have something where you do it in successive manners and the probability, you always replace it, like in a playing cards, or you replace the marbles back in a hat and shuffle it up again, the probabilities never change, whatever the events are. But if you keep taking something out of a deck of cards or a hat with different color marbles in it and don't replace it, the numerators and denominators are likely to change, and therefore the probabilities change as you do each successive trial. So here it is. Suppose you have a well-shuffled deck of 52 cards. It consists of 4 suits. The suits are clubs, diamonds, hearts, and spades. The clubs and spades are black. The diamonds and hearts are red. There are 13 cards in each one, consisting of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have the jack, queen, king. The 1 card is also considered the ace. 3 cards are picked at random. Suppose you know the picked cards are the queen of spades, king of hearts, and the queen of spades. Can you decide if the sample was with or without replacement? Well, it's hard to pick 2 queen of spades if you're not replacing it. If you're not replacing it. Because if I kept the queen of spades the first time, I got the king of hearts the second time, well, I can't pick those if I did not replace them the third time. I cannot pick, but I got the queen of spades again, so I had to have replaced the queen of spades to get it the third time. Suppose that you know the pick cards are the queen of spades, king of hearts, and the jack of spades. Can you decide if the sampling was with or without replacement? I would say here I couldn't tell the difference. I couldn't say for sure what it was, because if I didn't replace the queen of spades and never picked it again, or the king of hearts and never picked it again, I could get this queen of spades, king of hearts, and jack of spades. But if I also replaced the queen of spades and the king of hearts, I could still get the jack of spades and not necessarily repeat one of those 2. So in the first case, I could say this was definitely with replacement. In case 2, I could definitely say it was no conclusion. So, draw 2 cards from a standard 52 deck with replacement. Find the probability of at least 1 black card. Well, the probability of a black card is 50. It's a coin toss. It's the coin toss. So, what do I get? I get my set, if I look at it, is black, 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 red, red, black, red, red. Because each suit has 13 cards. So the blacks are spades and clubs. The reds are diamonds and hearts. So I don't care which. I'm just looking at the color now. That's my only choice. And what's the problem? This is my entire space. This is exactly what I can get. I replaced it so the probabilities are equally likely of getting each one of these. If I did it without replacement, it would change. It would be a much more complicated problem. So the probability of getting what here? At least 1 black card. At least 1 black card. Well, how many ways can I do that? There's 2 black cards. That's at least 1. That's at least 1. That's at least 1. So I'm going to get 3 out of 4. Or I'm going to get 0.75, which is also 75%. Now, versus independent versus not independent. Mutually exclusive is they cannot occur at the same time. This means A and B do not share any outcomes together. In that intersection space, they get the empty set. The probability of A and B happening at the same time is 0. If it is not known whether A and B are mutually exclusive, assume they are not until you can prove otherwise. So a student goes to the library. Let the events be the student checks out a book, and D, the student checks out a DVD. Suppose the probabilities are 0.4 and 0.3. It sounds like the German class again. Probability of taking German, probability of taking Spanish, but in this case it's a book and a DVD. The probability of B and D. B and D is 0.2. We know this. We're given this. This is a number you're given. So find the probability of, in this case, what do we want to say? Of B and, so we know that this is the probability of B and D divided by the probability of D. Well, what's the probability of B and D? It's 0.2 divided by the probability of D, which is 0.3, which is 2/3. What is this one? Well, this is going to be the probability of B and D. How do I remember this? I remember the formula that we had. Divided by the probability of B. Well, in this case, what's the probability of both? It's still going to be 0.2, but now it's divided by 0.4, and it becomes 50%. 0.2 divided by 0.4 is just 2 divided by 4, or 1/2, or 50%, or 0.5. Are they mutually exclusive? Well, I don't know, what was our definition of mutually exclusive again? The probability of A and B is 0. Well, the probability of A and B, they told us right here. Probability of A and B is not 0. So they are not mutually exclusive. So this answer to this is no. The probability of, are they independent? Well, the probability of B given D should be just the probability of B. Well, the probability of B is 0.4. We got 0.23 from our calculation, so they're not independent either. And if I did this one, the probability of D given B should just be the probability of D, but it's 0.5 and not the probability, and not 0.3. So they're neither independent nor mutually exclusive. You've got to understand. Independent means that's it, replacement without replacement kind of thing. If I flip a coin 2 times in a row, what's the probability of getting heads? Heads. Well, what's the probability of getting a head times the probability of getting a head? It's on each one. It's 1/2 times 1/2, or 1/4, or 0.25%, or 0.25, or 25%. Well, the other way of looking at it is if I look at the space, there is one way of getting head. If I look at flipping a coin twice out of 4 possibilities, which gives me, again, 0.25. So there's independent, and they're mutually exclusive, because the probability of getting a second head given the first head, it doesn't matter, still 1/2. The probability of, it doesn't matter. The probability of getting a head given I got a tail is still 1/2. So they're independent. And I can't get a head and a tail at the same time on anything. So a box has 2 balls, one red and one white, one red. We select one ball, we put it in a box, we select a second. Let T be the event of getting the white ball twice. Let F be the event of picking the white ball first. Let S be the event of picking the white ball in the second drawing. Okay, so what's my space look like here? Let's write this down. S. We can get white, white. We can get white, red. We can get red, white. We can get white, red, red. Okay? It's just like flipping a coin twice. I have one red ball, one white ball in a box. I I close my eyes, I pick one. I put it back with replacement. What does with replacement immediately tell us? They're independent. They're independent events. With replacement. Without replacement, they're not independent again. So it's like flipping a coin twice. It's like, it's just, what's the difference? If I use W's and R's or if I use T's and H's? Okay, so what's the probability of T? T is the event of getting the white ball twice. Well, this is equal to, I can only get the white ball twice once out of 4, so that's 0.25. What's the probability of getting, and what's F? The event of picking a white ball first. Well, the probability of, what is the probability of getting T and F? Well, what was F? So this is T, and F is picking a white ball first out of these two. That's this two events. So what's the probability of T given F? It's probability of T and F. Well, and the probability of F. Well, I have 2 ways out of 4 of getting this. And how many ways can I do this? Well, if I can't get T unless I did F first. So the probability of T given F is just the probability of T, which we already calculated, which is 1 out of 4. Which is, so it already told me I picked the first one. So I'm going to get 1 out of 2 here, or 0.5. Given that I picked a white ball first, there's only 2 of those events. There's only 2 ways that can happen. That's my reduced sample set, and there's only 1 way out of those 2 that I can get white. Are T and F independent? What are T and F? Well, no, it should be, we calculated the probability of T right here, and it's not equal to the probability of T given F, which is right here. So they're not independent. Are they mutually exclusive, F and S? What are F and S? F is picking a white ball first. S is the event of picking the white ball in the second drawing. Ooh. Well, how do we, are F and S mutually exclusive? What do you get for that? Well, what's mutually exclusive again? It means the events cannot occur at the same time. This means that A and B do not share any outcomes the same. The probability of A and B are 0. Well, I don't know about that. F and S. What is F? The event of picking a white ball first. So which ones are F? F are these 2. This is F. And what is S? The event of picking a white ball in the second one. The only way you can pick a white ball in the second one is this one. That's S. Even though you shouldn't use S for that, but that's okay. That's what they did. They used S for second, F for first. So that's F, and that's S. Well, they have something in common. They have the WW. So they're not mutually exclusive. There is one event, the intersection is not 0. Are they independent? Well, how do we get independence again? independent events mean, suppose you know that you picked, let's see, what was the definition of independence? We're doing it with replacement, are we not? These events are considered to be independent. So what do? The student, are they independent? So what's this? This is the red ball. So what's the first one? The event of picking a white ball first, the event of picking a white ball second. Well, how many ways can I think the probability of picking a white ball is always half. So the probability of F and S, let's write this down. Probability of F and S is what? The probability of, is it the probability of F times the probability of S? What's the probability of getting F and S? The only way you can get probability of F and S is to get one. You have to get white out of how many possible tries? 4. And then let's put this, is that equal? What's the probability of getting F? On the first one, I get, there's 2 out of 4. And on the second one, there's 2 out of 4. So I get 4 out of 16, which is 1 out of 4, which is 0.25. I'd say they're independent because I'm replacing the bowl. I put it back in the box, so it's independent. Okay, probability topics. 2 basic rules of probability. Yeah, we're on slide 24 of 46. So we're going to use the multiplication rule. Remember the rule. Probability of A given B is probability of A and B divided by the probability of B. If 2 events are, A and B are 2 events defined in a sample space, then we get the probability of A and B is the probability of B given the probability of A given B, or it's a probability of, so if the events are independent, the probability of A given B is the probability of A. If the probability of A and B is A given B times probability of B, then it becomes probability of A and B just becomes the probability of the 2 events times each other, like we just saw. The addition rule, when it gets to OR, if A and B are defined as on the sample space, then the probability of A or B becomes the probability of A plus the probability of B minus the probability of A and B occurring at the same time. If the probability of A and B are mutually exclusive, then the probability of A and B are 0. And so the probability of A and B just becomes the probability of A plus B. So mutually exclusive means the additive probability, the OR probability becomes an additive, and the conditional probability becomes, the probability of a successiveness. The probability of A and B becomes the probability of the 2 things multiplied by each other. Okay, what are we saying here? Independent means this. The probability of the 2 things A and B is the probability of A times the probability of B. Mutually exclusive means the probability of A or B just becomes the probability of A and B. Mutually exclusive means there's no intersection. There's nothing that you've counted twice. So a school has 200 seniors, of whom 140 will be going to college next year. 40 will go directly to work. The remainder are taking a gap year. 50 of the seniors are going to college to play sports. 30 of the seniors go directly to work, play sports. Also, out of the people that play, of the senior class, 50 of the seniors, how many players play sports. Well, it's 30, it's 50. This is one way of looking at it. 50 and 30 play sports. Because either they're going to college or they're not going to college, right? Those are mutually exclusive events. But playing sports straddles both. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. So it's 50 plus 30 plus 5 is the total number of what is the probability that a senior is taking a gap year? Well, how do we want to figure this out? 200 seniors, 40 of which are, so I have, what do we have here? 200 total seniors. $140 going to college. $40 going to work. I'm not sure what we mean by a gap year. What is a gap year? You take another year of education so you can go to a better school. And so if I subtract these two numbers, 180 from that, I left with 20. The other classification is gap year. So 20 are going in a gap year. So if I pick a senior from random, what's the probability of it being a gap year? Is 20 divided by 200, or 2 divided by 20, or 2 divided by 20, or 1 divided by 10, which is 0.1 or 10%. Right? 20 of 200 is 10%. Same thing. What is the probability the senior is going to college and play sports? Okay, so what do we have? We have 200 total. We have 140 college. We have 40 right to work. We have 20 in gap. And now out of these, what do we say? 5 of these play sports. 30 of these play sports. And 50 of these play sports. So this is the sports column. And this is all. Sports and not. Find the probability that a senior is going to college and play sports. So let's call it C for college, and I hate to use it, S for sports. So we want the probability of college and sports. What's that? It's the probability of, well, what do we say that was? This is a multiplication. We have the probability of college and sports. So it's the probability of B and the probability of A given B. Well, or we just do the counts. But what's the probability of A given B? So let's look at this. This is the probability of someone's a senior times the probability that someone plays sports given they're a senior. That's what we want. That's one way of looking at probability of being a senior And I think it's a probability. Let's make sure we do this right. Probability of senior and probability of sports being a senior times the probability of sports. Given they're going to college. Sorry. Okay. So what's the probability of sports? That's 85. That's how many people play sports over how many? 200. Times the probability of sports. Oh, I'm making this way too complicated, aren't I? What's this count? Let's make it easy. I'm really making this hard. Sorry. What do we have here? How many in this set? College, and they're going to college and they play sports. We have 50. How many do we have in the whole class? 200. So it's 5 over 20, or it's equal to 1/4, or it's equal to 0.25. There's no need to do anything else. We can just, because we can count all the parts. Student goes to the library, checks out a book. That's the event B. Probability D, same stuff we did before. The student checks out a DVD, and that's 0.3, and the probability of D given B. The probability that they check out a DVD given they checked out a book is 0.5. So what's A and B? Well, if we look at this, it's the probability of, what's the probability of, let's make sure we do it right. This is what I was trying to do last time and I messed up. So A and B is probability of B and A given B. That's very confusing. We got a lot of stuff here. So this is a probability. We've got the probability of D given B. And this is going to be the probability of probably B. B, A given B, yes. So this is probability of B. Well, what is that? Probability of B is 0.4 times probability of D given B is 0.5. What's 4 times 5? It's 20. Count 2 decimal places, 0.2. How about D or B? Well, we said this is a probability of B plus a probability of D minus the probability of B and D. Because I've got some D in here and I got some B in here. I don't want to double count that, so I got to subtract it out. So this is a probability of B and D, which we just decided that was 0.2. This probability of B was 0.4. The probability of D was 0.3. So that adds up to 0.7. So it comes out to be 0.5. First time you do this, you don't want it to be on an exam. Student goes to the library, checks out a book. Student B goes and checks out, the event is a student checks out a DVD. Probability of B is, again, 0.4. Probability of D is 0.3. The probability of D given B is 0.5. Is that what we got last time? Yeah, well, that's the same problem. What's the probability of B, the opposite of B, the B complement? Well, it's 1 minus the probability of B, which we know, equals 1 minus, and what was the probability of B? 0.4. This equals 0.6, or 60%. The probability of D and B, Did we not do that already? Isn't that 0.2 from last time? What's the probability of B given D? We had D given B. Now we're looking at B given D. Well, another way of looking at the probability of D and B, what we used last time was what? Probability of B times the probability of D given B. Oh man, I didn't mean to do that. This is going to be a long lecture. Well, let's see, what was it? Last time we looked at it, it was a probability of B and DB. Now we can also look at the probability of D times the probability of BD, which is the opposite. I know probability of D and I know the probability of D and B. I can figure this out by saying the probability I just solved for this equals the probability of D and B, which I know is 0.2 divided by the probability of D. What's the probability of D? 0.3. I get 2/3 or 0.667 or 66.7%. You got to be going crazy at this point. What the heck is this guy doing? So now when we talk about contingency tables, what do we got here? We calculate probabilities. Look at this. We got injuries in the last year. No injuries in the last year. These are some athletes that do stretching before exercising and how many had injuries within the past year. I think they say it's better to have stretching both, right? Before and after. But let's not. We got this. Injuries in the last year. 55 of these students had, or these athletes had injuries. And then 231 of them injuries last year. 55 from those that stretched. 231 from those that didn't stretch. A total of 286 injuries. No injuries last year, 295 that did stretches, 219 that didn't do stretches, 519. And the totals were 350, 450, and 800 as being the total number. So what's the probability of athletes that did stretching before exercises? So let's look at it this way. A. How do I use this table to do this? Probability. Stretch before. Well, how many stretched before? I had 350 divided by 800. Isn't that the total that stretched before? Okay, so I get this. I get 350 divided by 800. Or I get 35 over 80. What's 350 divided by 800? I get 0.375. 4.4375. I guess I'm going 4 decimal places. What is B? Athletes stretch before exercise given no injuries. Probability of stretch before given no injuries. Well, this is a probability of no injuries. Oh, I'm doing it wrong again. I'm going to make sure I look at it right so I don't screw up. Well, how many people, if I'm giving no injuries, that means, now let me change this to a blue color just so I can distinguish this one. No injuries means I'm restricted to this column only, and instead of 800, this is my total. So now my denominator is going to be 514. And what does it say? Athlete stretches before exercise and given no injuries. Well, that's 295 athlete that stretches out of 514. So what is 295 divided by 514? So I get 534. Let's make 5739. So where's my 5379? 53.79%, 53.8%. What we look at here is I want to decide which row, which column might be my row or column of interest, and then I want to figure out so that the total of that row or column becomes my conditional one. So it's given that there was no injuries, it told me I was operating in this column. Before they were saying how many athletes did stretches out of the total. Well, that many did stretches in total, and that many athletes in total. So that's the way I look at that. I got to decide what is my column and row, and what am I looking at. So here, this shows random 200 cyclists and the routes they prefer. Let M be males and H be hilly. So we had lake path, hilly path, wooded path. Then I had females, males, totals. So out of the males, what probability that a cyclist prefers a hilly path? So what is A telling me here? Out of the males, so it says the probability, I'm given that it's male, what probability preferred a hilly? So now it says, okay, I'm in this row. I'm interested in this total and how many preferred hilly. So it becomes, in that row, 52 males preferred hilly out of 90 total males, which is what? 52 divided by 90, or 578. Let's do 3 decimal places this time. 578, which is 57.8%. And then what's the next one? Are the events being male and preferring the hilly path independent? What does independent mean again? There's no intersection? Or is that mutually exclusive? Are they independent? Let's go back and look at our definition of independence. If A and B are independent, the probability of A given B equals A. Well, they're not independent because the probability of H given males is 0.578, and that's not equal to the probability of people that like Hilly, which is 90 divided by 200. And that's, I don't have to even do the calculation, 9 divided by, that's going to be less than 50%. So it's not independent. They're not independent. I think only males would have had to like the hilly paths for that to be true. Contingency column, try it too. Find a total in each row and column. I want you to do this yourself. What do we have? Weight, obese, normal, underweight, tall, medium, short. Add the totals of the columns. Find the probability that randomly chosen individual is from the tall group. Well, what are you going to do? You're going to divide for A. We're going to divide that by that. Find the probability that individual from this group is tall. Find the probability that randomly chosen individual is obese and tall. It means it has to be both, which means it's the whole group. Obese and tall is, now we're talking about this 18 right here divided by that total. Individual is tall given that the Fed is obese. Now we're restricted to this column. Find the probability that a chosen individual from the group is obese given that the individual is tall given obese. And then we said find the obese given that the individual is tall. That's E is the one I did. Find the person is tall given they're obese. We're in this row. That would be D. Find the probability that a random chosen individual from this group is tall and underweight. Tall and underweight would be 12 divided by this total. So you got to decide what row and column you're in, and then you're taking the numbers of interest divided by the total numbers in that row or column, or the total amount. So the given means, when you usually say when it's given, you're restricting yourself to a row or column in these contingency tables. Tree diagrams. Well, and Venn diagrams, I'm not a huge fan of Venn diagrams except to show things, some things. A tree diagram is used to determine the outcomes of an experiment. It consists of branches that are labeled with frequencies or probabilities, and they sometimes make it easier for, especially in conditional probability, to solve things. I don't like to, I don't draw them vertically, I draw them horizontally. Don't ask me why I do it that way. It's just the way I always have. So these are red balls and 8 blue balls, and without replacement. So we can at least, why are we listing each red ball? There's just 8 of them. So let's see. We draw 2 balls, one at a time, with replacement. The uninteresting one. And there are a total of 11 balls in the urn. Draw 2 balls, one at a time, with replacement. There are 11 times 11, 121 outcomes, or 64 the first time, plus 24, plus 24, plus 9. How does that work? Okay. Calculate the probability of getting red. Calculate the probability of getting red, blue, or blue-red. What's the probability of... But see, these probabilities are not going to change because you're replacing it every time. So it's really the probability of just getting red or blue. So what's the probability of calculating this? Let's go down here. All right, let's add another page here. All right, so how many red and blue ones are there? 3 are red, 8 are blue. And let me make this black so that I'm not confused with the colors. We have 3 red and 8 blue. Since there's 11 in total, probability of red is 3/11. Probability of blue is 8/11. Okay. I can calculate what that is if I want to in decimals. Now the first one they asked was probability of red. Red and red is what that is. But I know with replacement, they become independent events. So it's really the probability of red times the probability of red. It becomes a probability of 9 1/21 because it's 3 times 3. It's really 3/11 times 3/11. What was the other thing we had to solve? Either red blue or blue red. What's the probability of mixed? We can look at that. But it's really what's the probability of red the first time? Probability of blue the second time. Probability of blue times probability of red. Is it going to be, is order matter? Or is it just a matter of mixed colors? Do I care which way it goes? Let's not do that first. Red on the first draw and blue on the second draw. Red on the second draw given blue on the first draw. Well, given that they're independent, because we've done replacement, this one is simple. The very last one is very simple. Where is my little cursor here? There we go, here. This is probability of red given blue. That's the probability of red, which is 3/11. You can calculate the decimal places. So the only ones we really have to worry about are these two. Calculate red blue or blue red. Red on the first and blue on the second. Well, that's going to be 3/11 times 8/11, or it's going to become 24 121. And then are these two events independent? Which means there's no intersection of them. I think they are too. So that would just become double the probability of probably this one, which would become 48/11. So how do we do this? We have first draw, there's 8/121. And the second one, there's 3/121. You really want to divide these by out of 11, sorry. And these are all going to be divided by 11. Because, why? I'm replacing them all. First time I have a choice of getting a blue or a red. Second time I have a choice of getting a blue or a red. I have a choice of getting a blue or a red. So, and I have, when I multiply these all out, 8 times 8 is 64, but it's out of 121 divided by 121 divided by 121 divided by 121. So the probability of getting a red is 9, 3 11ths times 3 11ths is 9 121st. The problem of getting a red first and then a blue is 24. See, these two are the same. It's just going to be 2 times 24 over 121, or it becomes 48 over 121. And the probability of getting blue is 64 out of 121. So they didn't actually divide by the, they didn't put the denominator in. And so each one of these branches, this is the conditional probability of getting a blue given you picked a blue first, and the probability of getting a blue given you picked a red first, it's still going to be the same, 8 out of 11, because we did replacement. The probability of getting a red given you picked a blue, 3 out of 11. The probability of red, every time the probability of getting a red at any stage. Now to get to the final total of what's the probability of red, blue, blue, red, blue, I multiply these together because they're independent of each other. So easy to calculate. Now, without replacement, it becomes a much different problem. Because look at this. What do I have here? I have 8 out of 11, 3 out of 11. Well, that's the same as the first one, right? 8 out of 11, 3 out of 11. But now, to go to the next step, blue given I picked blue, what do I get? I get, now one blue's missing and there's not 11, there's only 10. So it becomes 7 out of 10. Now to multiply them together, it becomes 7 times 8 times 10 times 11. It becomes 56 out of 110 to get blue. To get a red, given that I picked a blue the first time, there's still 3 red ones, but there's only 10 left. To get a blue, given I picked a red one the first time, there's still 8 blue ones, but there's only 10 left. So all the denominators at the second pick are 10, and the numerators go up or down depending on what the first pick was. To get to this level, how did I get red, 6 out of 110? How to get red, blue, 24 out of 110? Well, these two are the same again. This tends to happen. And then to blue is this one. So how do I answer these questions? Probability of red, 6 out of 110. You can do the, put it in your calculator and get the percentage if you want. Red, blue, or blue, I add these two together. So I get 48 out of 110. Red on the first draw and blue on the second. Red on the first draw and blue on the second is 24 out of 110. Red on the second draw given blue on the first would be 24 out of 110. So, or given blue on the first one. So yeah, the mixed one. That's how that works. A Venn diagram it shows the intersection of two things. So let's look at one of the original things we looked at. We had the set A, 1, 2, 3, 4, 5, 6, and the set B, 6, 7, 8, 9. Oh, it's not the same one. But here, draw A. We draw a circle around A, and then we had the whole set is the numbers 1 through 12. So we draw a circle around 1, 2, 3, 4, 5, 6, and then B is 6, 7, 8, 9. So we draw a circle. Notice that the circle overlaps on the intersection, the things that the two have in common. And then these 3 numbers are not in either one. So A and B is equal to just 6. A intersection B is that. The A or B is 1, 2, 3, 4, 5, 6. Well, 6 is in B. I don't count it twice. 7, 8, 9. And that's a Venn diagram. So 40% of the students at a college book club belong to a club, and 50% work part-time. 5% of the students work part-time and belong to the book club. Draw a Venn diagram. So let's pretend it's 100 students. So we know that if we come down here, what do we say? Let's say it's 100 students. So we're not confusing ourselves with percentages. We said 5 do both. 5% of the students work part-time and belong to the club. The club has 40% of the students, so 35 of the students are here. So if I add 35 and 5, I get 40. And 50% work part-time, so I have 45 here. How many are in both these? Well, I have 40 and 45, 85%. So 15%, 15 of the 100 students are out here. What's the probability the student belongs to the club? So what's the total number? Is 40 out of 40%. The student works part-time. What's the probability that the student works part-time? It's going to be 50 divided by 50%. The student belongs to the club and works part-time, 5 out of 100, 5%. The student belongs to the club, given that the student works part-time. So now I'm going to have, given that the student works part-time and belongs to the club, that's going to be 5 out of 45, or 5 out of 50. Given the student belongs to the club or works part-time. Well, it's going to be 35 plus 45, which is, what is that? 70, 80. And I only add the 5 once. So rather than add the 40 and 5 and getting 90, I'd do 85 divided by 100. And basically, I think that's it. So, sorry for this long-winded lecture and all the bad writing and all that, but this is kind of how it works. And we'll talk again. We'll cover this in class, and mostly we're going to go through problems so you see how to do this.